Hey everyone, welcome back to the channel. Today we are diving deep into the worlds of the threads and the processes by walking through a simple Java program. But this video isn't just about running code. We are going to uncover how Java actually runs under the hood. What is a process? What is a thread? How is memory shared? How does the CPU manage multiple threads? Stick with me, and by the end of this video, you will have a crystal clear mental image of how Java works from code to execution. So let's begin. Alright, let's start with a simple Java file. Let's say test.java. When you write your code in Java, the very first step is to compile it using the JVM command. Think of this as translating English into a universal language. The Java compiler takes your readable code and convert it into something called bytecode. This bytecode is stored in .class file and it is not tied to any of the operating system. So let's say we have 3 operating systems. So basically, bytecode is a neutral format that any machine can understand that contains a JVM. It's not like you can run the bytecode in a given operating systems. You can run the bytecode in any of the operating system given that that particular operating system contains JVM. JVM is the Java Virtual Machine. Now you take that bytecode and run it using Java test. This is where magic happens. When you do this, this command asks your operating system to start a brand new process. Think of a process as program's own personal isolated environment. It gets its own memory, system resources, and a private space to run. Inside this particular process, OS loads a JVM instance. You can think of JVM as Java's own operating system sitting inside your OS. The JVM takes responsibility for managing memory, loading classes, creating threads, and running your bytecode. Now, this particular JVM instance contains JIT, that is just-in-time compiler, which will help you to convert the bytecode into machine code so that JVM can execute this machine code. What we have done is we create a separate area, provide a separate OS, provide separate resources so that a process can run independently. So basically, multiple processes get its own JVM instance and the private space to run, so that each process can run independently without interfering with each other. Now, every JVM needs memory to do its job. Now, what we have seen is operating system contains the JVM and the process contains the JVM instance. This particular JVM instance, the instance is the same as we have read in the class and the object concept. We have a class and we try to create an instance of that particular class to create an object. Now, while creating a particular object, you pass some parameters in the constructor to initialize the object. Similarly, to initialize the JVM, you pass some memory parameters. Now, while creating a particular process or while executing a bytecode, you try to pass some flags, that is -xms and -xmx. So basically, -xms 256M starts the JVM with 256 MB of memory, and -xmx 2G lets it grow up to 2 GB if needed. Now let's talk about how the threads are created when they are created. Now, when your Java program start running, the JVM automatically creates the main thread. This is the thread that runs your public static void main function. So basically we create a main thread. From this main thread, you or the libraries you use can create more number of threads. These threads all live in the same process and share the same JVM memory. So let's say for a given main thread, we create two subthreads, thread 1 and the thread 2. Both the threads will be occupied in the same JVM instance inside the process. So let's say this is the thread 1 and this is the thread 2. This is where Java's multi-threading power comes into play. Multiple threads can work together, sharing data, but also working on different tasks simultaneously. Now, this particular JVM memory is divided into 5 regions. So let's talk about it one by one. So the first one is code segment. This is the area where the compiled machine code goes. JIT compiler convert the byte code to the machine code and stored it into the code segment area of the JVM. So this is the code segment. This particular area is read-only and shared among all threads. So from this architecture, you can easily see that this particular thread 1 and the thread 2 share this code segment in this particular block also. We will see what this block denotes. Now let's move to the second area, that is data segment. This particular area stores global and static variables. All threads can access this data segment, so proper synchronization is required. So basically, this is the data segment. The third area is heap memory. This is the largest part of the memory where all the runtime objects are stored. Here objects are created with a new keyword and it's shared among all the threads. So this is the heap memory. Now let's talk about the stack. Now the stack memory. Now this particular stack memory is specific to a given thread. So basically each thread has its own stack memory and it is used to handle function calls and local variables. So this is the stack. Next is program counter. This area holds the address of the next instruction to execute. This particular area also specific to a given thread. And this is the program counter and this is the program counter. And the last one is registers. This is the area which is used to hold intermediate values and temporary results during instruction execution. So this is the registers. Don't worry, we will look into a sample code how the data is populated in this particular memory and how the threads are created and how multi-threading works. From this, what we have learned is what we have learned is that a thread is a part of a process. And a given process can have multiple threads. So basically, thread is a lightweight process. So when bytecode is converted into machine code, this particular machine code contains many lines of instructions. For example, if there are 10 lines of instructions, we split into multiple parts and assign each subset to a given thread. So let's say we assign this instruction to thread 1 these instructions to thread 2. When a process is created, it starts with one thread known as the main thread. And from that, we can spawn multiple threads to perform tasks concurrently. Therefore, if a process has 3 threads, the main thread and the 2 child threads, and we have a dual core CPU, then 2 of the 3 threads can be allocated, 1 per core, and the CPU executes each thread's assigned instruction simultaneously. So basically what happens is OS create a particular process create multiple threads, and if I have dual core CPU, then both the threads can run parallelly on different cores. Alright, now let's take an example where we demonstrate how multithreading works in a single core CPU. So when the program begins, the operating system creates the main thread and put it into the ready queue. A stack frame is allocated to this particular main function with local variables T1 and T2, which are currently uninitialized. The CPU registers will contain the program arguments plus return address. And the program counter points to the first instruction of the main function. We have already discussed that machine code instructions live in the code segment area. So the program counter contains the address of the next instruction. So this particular address contains the address of the instruction that is present in the code segment. After that, OS scheduler picks the main thread from the ready queue. It loads the main's register values and the stack values into the CPU. Now currently the main thread register contain nothing, but the stack contain T1 and T2. So the register contain T1 equal to null, T2 equal to null as of now. And now the CPU program counter point to the next instruction, that is thread T1 equal to new thread. Now after executing these 2 lines, the main stack now contains T1 and T2, both are referencing to new thread object. The CPU registers only hold those references temporarily during the assignment. The permanent storage is in the stack. So the T1 will contain the reference of the object, and the T2 also contain only the reference of the object, but the actual storage will happen in the stack itself. And now the program counter of the CPU will point to T1.start. Now after executing T1.start, the JVM creates a new thread T1. A new stack frame is allocated to T1, and the program counter will point to do work 1. At this point, T1 stack contains id equal to 1. The loop variable I is not created yet, and the T1's registers will be currently empty. Meanwhile, the CPU program counter will move to the next instruction, that is T2.start. After executing T2.start, it does the same process for the thread 2. A new thread is created, a new stack frame is allocated, the program counter points to do work 2, and the stack contains id equal to 2. And the program counters of the CPU move to the next instruction, that is T1.join. Now one thing we have missed, that after we create the thread 1 and the thread 2, the OS will put it into the ready queue also. Now after that, when CPU executes T1.join, the main thread enter into the waiting state until T1 finishes. The OS scheduler removes the main thread from the ready queue. And then CPU's program counter and the register values are stored back into the main thread so that we can resume later. So basically, the program counter of the main thread will contain t2.join. The stack will remain as it is and the register will contain nothing. After that, OS scheduler pick T1 thread and loads its program counter and the register and the stack values into the CPU register and the program counter. So now what will happen is these values will be removed. Now the program counter of the CPU will contain do work 1 and register contain id equal to 1. Now at the time of the first iteration, I equal to 1 is created in the T1 stack plus in the register also, and then a print statement is executed. After that, program counter will advance to the next iteration, that is the next loop. Now suppose the time slice ends and the context switch occurs. In that case, T1 state is saved. So basically what we do is we save the register and the program counter values of the CPU back into the thread 1 program counter register in the stack. So the values will look like this. Now the operating system scheduler pick the thread 2. So what happen is we just load the program counter register and the stack values of the thread 2 into CPU register and the program counter. So what will happen is the CPU register will contain id equal to 2 and program counter contain do work 2. The register of the T1 contains nothing as of now. Now after the first iteration, I equal to 1 is initialized and it will be initialized in the stack frame also. It print the first line and then let's say a context switch again occurs and control again goes back to the thread T1. So we just save the register and the program counter values back to the thread 2 and load the existing values of the thread T1 into the CPU registers. So we will just remove it. We update the program counter of the thread 2 and we load the thread T1's values into the CPU register and the program counter. That is id equal to 1, I equal to 1, next loop. Now after 2 iterations, T1 print both the lines. At the exit, I will become 3 because that is the condition that we have mentioned, that when I is less than equal to 2, it will print the lines, otherwise it will move out of the loop. So the I equal to 3 will be updated over here also. Now because the do work function ended for the thread T1, the thread T1 will be terminated and the stack frame is popped. The registers and the program counter space of the thread T1 will be reused by some another work. And because we have blocked the main thread because of the T1.join, the main again move back into the ready queue. So what happened is we remove the thread T1, we put the main thread back into the ready queue, we remove the thread T1 values, and now the ready queue contains T2 and the main thread. Now here OS scheduler can pick any thread, either T2 or the main, because both are in the ready state. Now let's suppose scheduler picks main thread. So scheduler will load the register stack and the program counter values of the main thread into the CPU. So we remove these values and we put T1 equal to that reference, T2 that reference, and program counter contains T2.join. After executing T2.join, main again move to the waiting state. Now the ready queue contains only the thread 2, so OS scheduler pick the thread 2 and execute the last iteration of the loop. So after executing the last iteration, what happen is thread 2 also get terminated, the stack frame of the thread 2 will also get popped out, and the register and the program counter space will be reused by some another work. So what happen is we remove the thread 2, we remove the space that has been occupied by the thread 2, and we put the main thread back into the ready queue. Now the operating system scheduler doesn't have any choice. The ready queue contains only the main thread, so it will pick that particular main thread, loads its values into the CPU registers and the program counter. Now the register value will not change, but the program counter now point to the last line of the instruction. That is the print statement. Now after executing this particular print statement, that is the main T1 and T2 have both finished, the main thread also get terminated, the stack frame of the main thread will be popped, and the space for the register and the program counter will be reused by some another work. When no threads left, the JVM exits. So this is how multi-threading works when you have more number of threads than the number of CPU cores.